So far we have seen what are complex valued functions and how we do calculations with those complex valued functions by writing them down as u plus iota v. Now we want to see if we can get geometrical representations of these complex valued functions. Now why do we want to get geometrical representation? For one reason, we want to observe properties of these complex valued functions using geometry of them, and on the other hand it will give us some very beautiful pictures. So on the screen we can see the geometrical representation of a complex valued function, which we will see in future. Now how do we get geometrical representation of functions? So for that, let's go back to calculus of functions of one variable. So given a function y is equal to f of x, we have this curve associated to this function. Okay, so what's the procedure for associating this curve to this function? Okay, so we have the input of this function, which is on the horizontal line, which is the real line, and the output of these of this function is plotted against this real line, which is the vertical real line. And how do we get this curve? So for each point on the domain we have the output. Okay, so for 3 we have this output. So this output is basically correspond to a point on this range axis. So the output of 2 is, for example, 4. So this point is 2, 4 in the plane. Similarly, we have outputs of other points in the domain, and when we join them we get a curve in the plane. And from this curve we can observe many properties of the function. For example, we can see that the function is increasing from this point to this point, and this is the local maxima, and from there onwards the function starts to decrease, and this is the local minimum, and up to so on. And we can also observe that the function is smooth, so we can say that the function is differentiable, etc, etc, etc. So there are many properties that you can observe from by just looking at the graph of the function. So it's a very useful thing to have a geometrical description of a function. Now let's have a look at the question that can we have similar geometrical description of the function for complex valued function. Now for complex valued function, the domain z is a point in the plane. So in other words, it's a point in R2, and similarly the output, which is another complex number, is a point in R2. So following the same procedure as we did for real valued functions of one variable, so we take the domain axis and we take the range axis. So in this case the domain is coming from a plane R2 and the range is coming from the plane which is R2. So if we follow the same procedure, then the graph of these functions are going to be in R4, which is kind of very difficult task. Okay, so to observe geometrical properties from the graphs in R4. So what is the solution of this problem? So the solution is very simple. We take the input plane as Z plane and we take the output values in another plane. So in other words, we take points from this plane and we plot them in another complex plane. Okay, so we take values from here and we plot them in the W plane. So we have two different planes, one for the domain and one for the range. The domain plane is called the Z plane and the range plane is called the W plane. So when we consider a function using such correspondence between two complex planes, the Z plane and the W plane, then we call complex functions as complex mappings or just mappings. So we know that a function can be written as u of xy plus iota v of xy, where u and v are real valued functions. So in this case, the domain plane, which is the Z plane, has two axes, the x-axis and y-axis. And we apply, okay, so u on a point of this Z plane and we get one real number and we plot them against this horizontal axis in the W plane. And similarly, when we apply v on this point xy, we get another real number and we plot it on this vertical real line, which is the v-axis. Okay, so that's how we get image of a point xy from z plane to the w plane. Now let's consider a simple example where we have the function f of z is equal to z plus 1 and the domain of the function is this unit closed disk. Okay, so if we apply this function on 1, we get 2, and if we apply this function on iota, we can easily see that iota plus 1, and if we apply this function on minus 1, we get 0, and when we apply this function on minus iota, we get 1 minus iota. Similarly, we can calculate the images on other values from the domain of the function. Now let's try to plot these values from z plane to the w plane. So in the z plane, we calculated the images of 4 points. So one of them is 1, the other one is iota, minus 1, and minus iota. And of course, we can see that these are points from the domain of this function. Okay, so this is the domain of the function. Now, these are the points from the domain. So what are their outputs in the w plane? Okay, so this is the w plane. This is 1, 2. Okay, so iota, 2 iota. Okay, so let's see what are the images of these points in the w plane. So the image of 1 is 2. The image of iota is 1 plus iota. The image of minus 1 is origin, and the image of iota is image of minus iota is 1 minus iota. So if we join these points and if we calculate the images of other point, then we get the following disk. Okay, so if we start from this domain D, which is the unit closed disk centered at the origin, then we get the following. So the image is the disk centered at 1 and the radius is 1. So we can say that from this geometrical representation of the function, we can say that this function is translating the points of the domain to the right 1 unit. Okay? So similarly, if we have other subsets of the domain, so consider this set A, which is a disk, closed disk of radius 1 by 2 and center origin, then the image of this disk is another disk which is centered at 1 and the radius is 1 by 2. So geometrically, how do we represent it? So we represent it in the following way. So this is the set A, which is the disk, and the output of this or the image of this disk is this basically this disk B. So this kind of geometrical representation of the function help us in understanding the behavior of the function. So sometimes it is useful to represent both the domain and the range in the same plane. So for example, in this case, this is the domain and this is the range disk, and we can easily see that the domain disk is translated to the right 1 unit when we apply function on the domain. So in general, if we have a function and this is the domain and this is the range and this is subset A of the domain, then if we apply function on A and if we get the values B, then we say that this function or the restriction of the function is from A to B. And of course, the points on the domain get images in the range. Okay, so if this point is Z, then we have this f of Z. Now, the next question is, we know that a function is a procedure that takes Z as inputs and give us W's as output. So it's a kind of box that processes this Z and gives us output as W. Now the question is, can we find the reverse procedure of this process? Okay, so can we find the inverse procedure of this function f of Z? Unfortunately, the answer to this question is, in general, this is not possible. But fortunately, there are some conditions on the function under which the inverse procedure of this process exists. So what are those conditions? So for that, let's observe few examples. So in this case, we have a simple function f of z is equal to iota z. So when we apply this function on the points on the domain or the z plane, we get points in the w plane. So in particular, when we apply this function on the point iota, we get the point -1. And no other point from the z plane maps to the point -1. So in other words, we can say that the inverse image of -1 is iota. Now in this case, when we try to find the reverse procedure of this function f of z, then it is possible, because the inverse image of -1 is iota. And if this happens for all the points in the range, that the inverse image of each point is unique, then it is possible to find the inverse process or the inverse of this function f. Now let's see where the existence of inverse is not possible. So consider this function f of z is equal to z square. Now in this case, the image of iota and minus iota is -1. So when we try to find inverse function or inverse procedure of this function f, and we normally represent this inverse function by f raised to power -1. Now in this case, it is not possible. So why it is not possible? Because by definition of function, a function should give us a unique output, which in this case is not possible, because the inverse of -1 is basically not unique, and it is 2 points iota and minus iota. So we can say that in this case, the reverse or in reverse procedure of f or the inverse of the function f does not exist. So in other words, we should have unique output for each and every point in the range. Okay, so when we apply the reverse of f, so we call such condition as one-to-one condition. So we say that a function is one-to-one if a unique points in the range gives us inverse images as unique point. Okay, so precisely speaking, when a function is one-to-one, so a function is one-to-one if we assume that f of z1 is equal to f of z2, where z1 and z2 are 2 points in the domain, and if this implies that z1 is equal to z2, then we say that function is one-to-one. So in other words, what this condition is saying, so this condition is saying that the only way that the functional values are equal is the condition that the input values are equal. Okay, so if f, the function, is not one-to-one, the inverse image of a point is not unique. Let's consider a few examples where we want to observe that if the function is one-to-one or not. So consider this function f of z is equal to iota z. The question is this a one-to-one function? Okay, so once again, our condition is we start from f of z1 is equal to f of z2, where z1 and z2 are any arbitrary points of the domain. Now applying this function f on z1, we have iota z1, and applying this function on z2, we have iota z2. Now this implies cancelling out this iota, we get z1 is equal to z2. So by definition, f of z1 is equal to z2 implies z1 is equal to z2. So this function is one-to-one. Now consider another example where we have the function f of z is equal to z square. Now this function is not one-to-one, okay, because we have two values of z1 and z2. So one of them is iota and the other one is minus iota, such that f of z1 is equal to f of z2. So remember that f of z1 is -1 and f of z2 is also -1. But this does not imply that z1 is equal to z2, since z1 is iota and z2 is minus iota. So iota is not equal to minus iota. So we can say that this function is not one-to-one because this condition is not satisfied. Okay, now the point is, if we have a function which is one-to-one and onto the set B. Okay, so this is the set A, this is the set B, this is in the Z plane, and this is in W plane. So onto means each and every element of B is mapped by some point of A. So if this is a function which is one-to-one and onto, then we can define the inverse function of this function. So it will satisfy both conditions of the definition of the function. So what are the conditions? That each element of B is mapped to a unique element of A. And why each is covered? Because it's an onto function, and each and every element of B is image of some element of A. So that's why each element of B has a unique image, because it is 1 to 1. So there must be a unique element in A. So in this case, if function is 1 to 1 and onto, then we have inverse function. How to calculate that inverse function? So let's see. So if we are given W is equal to f of Z, then we try to solve Z in terms of W. And we can do that because the function is 1 to 1 and onto, and when we calculate that, then we call it the inverse function. Z is equal to f inverse of W. Now mathematically speaking, what are the conditions under which we say that if function is inverse of a given function f? So these are the two conditions that define when we say that a given function is inverse of the function f. Okay, so the condition is when we start from Z and apply f, and when we apply f inverse on this f of Z, then we again get the same point where we started from. In other words, these f and f inverse kind of cancel out each other, and they are inverse process of each other. And similarly for W, when we apply f inverse first and then we apply f, then we again get W, which is the starting point in this case. Okay, so in other words, if we are given a function which is this box, and we are given inverse function which is this box, then when we take output from this box and when we put that output as input to the inverse function, then we again get the same output which was our initial input. Okay, so similarly the other procedure when we start from f inverse and f. So these are two mathematical conditions that say when a function is inverse. Now given a function f of Z is equal to iota Z, this is 1 to 1 function and onto function onto the entire complex plane. In other words, the domain is the entire complex plane. So we can calculate the inverse of this function in a very simple way. So in this case, W is equal to iota Z. So from here we can easily find the value of Z in terms of W. Okay, so Z can be expressed as a function of W. So this is our inverse function. Okay, so f inverse of W is equal to minus iota W. So sometime we write down the same variable for the inverse as we write it down for the function. Okay, so in this case f inverse of Z is minus iota Z. And of course it is a simple exercise to see that these f and f inverse satisfy these two conditions. Now calculating inverse help us in understanding the geometrical representation of function. Now what is the procedure for observing the geometrical behavior using Z plane and W plane? So the idea is we take subsets from the Z plane and we observe their images in the W plane, and based on those images we try to understand the geometrical properties or the behavior of the function. So let's consider a very simple function f of Z is equal to minus Z, and in this case we choose the following set A, which is a straight line, and we try to calculate its image. Okay, so we can easily see that in the Z plane it is a straight line. This is the point 1. So this is y is equal to minus x plus 1. Now if we want to calculate its image, then we need to calculate the inverse of this function, and we can see that the inverse of this function is also the same function minus Z. So they are inverses of each other. Now we want to calculate what are the points u plus iota v such that they belong to the image B, and B is equal to f of A. Okay, so this is only possible when we apply inverse on this W and we get points of A. Okay, so f inverse of W, so we can see that f inverse of W is minus W, and from here we have minus u plus minus iota v which belongs to A, and this says that minus u minus v belongs to A, and using the condition we know that a point belongs to A if the y coordinate should be equal to minus into the x coordinate plus 1. In other words, we have the condition that minus v should be equal to u plus 1. So from here we can observe that given a line in the z plane, which is this set A, the image in the w plane is another line, which is this line. So this tells us something about the about some properties of this function, that it takes these lines and it reflects them on this line. Okay, and similarly, if we change this set A, then we get other information about the behavior of this function f. So we have seen how we can associate geometrical depiction of a complex valued function. Okay, so using this we can observe different properties of functions. In our next discussions, we will choose some very special complex valued functions, and we will try to observe their properties by looking at their images in the w plane.